In this talk, I'm going to go through an example of nodal analysis which is approximately at exam level. The kind of circuit that I would hope everybody would be able to solve by the time we get to the end of the module in the amount of time that you have to do it in an exam. And the circuit we'll be looking at is this one. 3 resistors, 2 voltage sources and a current source. 3 nodes which are not at ground, so we have a total of 9 unknowns to try to solve for. The voltages at the 3 unknown nodes and the currents through each of the 6 components. In general, solving a set of 9 simultaneous equations in 9 unknowns is very tedious, so we're going to be looking for shortcuts. First thing we need to do is to label all of the nodes and all of the currents in our circuit. We'll start off with the 2K resistor here, and we'll label the current flowing through this one as being I0. That goes up to a node A, which will be at voltage VA. Now, first shortcut. This is a voltage source. A 7 volt voltage source. If I was step by step following the instructions completely, I would have to label the current through this voltage source as a different unknown, and then apply Kirchoff's current law at node A, which would tell me that the current through the 2K resistor flowing in was equal to the current flowing through the voltage source flowing out. However, I can short-circuit that process just by saying, but it's obvious that the current flowing up through this resistor will be flowing through this voltage source because it's got nowhere else to go. I can just define this current as being I0 as well. That reduces the number of unknown variables by 1. Good start. Every little helps. Next, we have a current source. A 2 milliamp current source. Again, if I was just blindly following the rules, I would have to label the current through this current source as another one of my unknown variables, and write an equation for it stating that this current is equal to 2 milliamps, because that's what the current source does. I can short-circuit that process and just define the current going up through it as the known 2 milli, rather than having it as another unknown variable in my set of simultaneous equations. Moving on, I have a 3K resistor, and I can't do many tricks with that one. I'll just have to define the current through this one as being an unknown. I'll call it I1. And similarly, I have a voltage source down here. Now, if the voltage source here is 1 volt, then I know what the voltage at this node is going to be. I don't have to give that a variable name. I can just say, I know this is at 1 volt, because that's what this voltage source does. Maintains the voltage at that point as 1 volt above ground. And then I have a resistor here of 1K. And I'll need to work out the current going down through that resistor there. I'll call that I2, and there'll be a current flowing down through this voltage source here. I'll call that I3. This is node B, this is node C. I know node C is at 1 volt. Right, start to apply the equations for these components. Applying Ohm's law for this resistor tells me that the voltage here minus the voltage here is the current flowing from here to here times the resistance 2K. So this is the voltage at this point, where the current starts, 0, minus the voltage at this point, where the current goes to, A, equals the current, I0, times 2K. And I've taken care to get the directions right. The current is flowing from here to here, so the potential difference is the potential here, the voltage here, minus the voltage here. Then, applying the voltage source equation to this voltage source here tells me that VB, the voltage at B, minus VA, the voltage at A, is 7. That's what this voltage source does. It maintains the voltage here at 7 volts above the voltage here. That's my second equation. This resistor here gets Ohm's law applied to it as well. The current is going in this direction from node B to a node at 1 volt. So I could just write that as VB minus 1 is equal to I1 times 3K. I've got to apply Ohm's law to this resistor as well, but I know the voltage here, it's 1 volt. So the current is flowing from 1 volt to 0. So the voltage across this resistor is 1. That just gives me 1 equals I2 times 1K. And from this, I could instantly see that I2 must be 1 milliamp. You may have been able to spot that already. Then, I've got to apply Kirchoff's current law to nodes B and node C. I don't have to do it at node A because I already know the current flowing in is equal to the current flowing out. I gave them the same name. But I do have to apply it at node B and node C. At node B, the total current flowing in, I0, is, or rather I0 plus 2 milliamps, got two currents flowing in, is equal to the total current flowing out, which is I1. And for node C, the current flowing in is I1, and the total current flowing out is I3 plus I2. We've just worked out that I2 is 1 milliamp, so I could just write that as 1 milliamp. Now, I2 only appears now in this equation. We've got 6 equations here in 6 unknowns, which is rather better than the 9 equations in 9 unknowns that we could have had. I2 only appears in this equation, so we don't need to consider that equation anymore. Looking at where, that shouldn't be A, that should be VA, the voltage at A. Sorry. Looking at where I can get rid of some of these other variables, VA only appears in these two equations. So I could substitute in from here into here and get that VB plus I0 times 2K is 7, because VA is minus I0 times 2K. And that gets rid of VA. I've then only got VB appearing in these two equations. So I could say that from this equation, VB is 7 minus I0 times 2K. And from this equation, VB is 1 plus I1 times 3K. And I've got a set of 3 equations now. This one, in this one, in 3 unknowns, I0, I1, and I3. I3 only appears in this equation. So this equation and this equation are 2 simultaneous equations in 2 unknowns. That's much easier. From this equation, we can see that I0 is I1 minus 2 milliamps. So substituting that into here gives us 7 minus I1 minus 2 milliamps times 2K equals 1 plus I1 times 3K. Multiply out this bracket, we get 7 minus 2K times I1 plus 2 milli times 2K is just 4 equals 1 plus I1 times 3K. 7 plus 4 minus 1 is 10. Move this over to here, we would get 5K times I1, and therefore I1 is equal to 2 milliamps. That's the kind of nice round number that makes you think you've probably got it right. At least if this was a real exam question. If this was a circuit, of course, a real circuit, then the chances of you getting a nice round number like that, pretty minimal. Once we've got one unknown variable, we can substitute in and find all of the others. I1 equals 2 milliamps here, so that would mean that I0 was 0. A little bit surprising perhaps, but that is what the maths is telling us. I0, 0 milliamps. I3 is I1 minus 1 milliamp, so that would tell us that I3 was 2 milliamps minus 1 milliamp, or just 1 milliamp. That only leaves I2, and we know that I2 is 1 milliamp. So we've now found all of the currents. We can work out the voltages. From this equation here, we know that VA is I0 times 2K times minus 1. I0 is 0, therefore VA will be 0 as well. If VA is 0, then VB must just be 7 volts. And VC, we already knew, is 1 volt. So, we have solved it. It is fairly tedious. It's very easy to go wrong. But when you do get nice round numbers like this, at least in an exam, you'll get that feeling of confidence that you're probably on the right lines. Since we're not in an exam, we can check it. We can have a look on the simulator and see what it thinks. First of all, let's look at the currents. Yep, looks like the currents through these components really are 0, which means that the current through the 3K resistor must be 2 milliamps, because all this 2 milliamps is flowing this way. And we know the current down here is 1 milliamp, so the current down here through this voltage source must be 2 milliamps minus 1 milliamp, 1 milliamp as well. And for the voltages, well, if there's no current through this 2K resistor, there'll be no voltage across it, so the voltage here must be 7 volts. Easiest way to check that is probably to turn on Show Voltages. Yep, this point is at 7 volts, this point is at 0, this point is at 1 volt. We got it right. As you can see, that type of application of nodal analysis, even for a comparatively simple circuit, is quite tedious and error-prone. So, in the next videos, we're going to be looking at some shortcuts, some ways that we can solve for the currents and voltages in a circuit without having to go through the full nodal analysis technique and solving all of these simultaneous equations.